Hello, everybody. Welcome back to the afternoon session. So in this session, we have 3 talks, and we will start with the first talk about implementation security of quantum key distribution transmitters, and Feng-Yu Lu will give the talk.
Good afternoon, everyone. I'm Feng-Yu Lu from USTC. Today, my topic is implementation security of quantum key distribution. This topic is one of the most important foundation of QKD's practical deployment. As we know, QKD provides unconditional security against any attack in channel. However, it assumes the perfect sources and detectors. If the practical devices have loopholes, the QKD may not secure anymore. A famous example is the first QKD experiment in 1989. Due to the technical limitation, the device may have different noise when modulating different states. Regarding this problem, Professor Bassard remarks that our system is unconditional secure unless the eavesdropper happens to be deaf. So here I want to introduce several security problems. My first topic is induced photorefractive attack. I call it IP effect, and based on this effect, we designed an IP attack and and we demonstrated the first hacking experiment against a running MDI-QKD system. As we know, the lithium niobate devices are important components for current QKD systems. Due to their property of high speed and accurate modulation, they are widely employed as variable optical attenuators, intensity modulators, phase modulators, or polarization modulators. We can claim that the implementation security is tightly relied on the property of LN devices. So what is the induced photorefractive effect? It is the intrinsic property of the LN material. Irradiated laser in the material may generate charge pairs. Then the charge pair transfer and redistribute under the DC bias signal. And finally, the redistributed charges build an extra charge field. The charge field performs as an DC bias error. It may lead to unexpected refractive index change and unexpected modulation result, and consequently bring us potential loopholes such as more multiple photos, misaligned encoding, and misaligned basis selection. So our IP attack can be described as follows. Here, we can the eavesdropper use an irradiated laser to inject a laser from channel to users' LN devices and control users' output intensity. If the intensity is under eaves control, the important decoy state method may not valid anymore. So here is our test devices. This is our hacking performance. We can find here is the injection stage. In this stage, we increase the laser power. So the user's output intensity change dramatically. Here is the stabilizing stage. At this stage, we control the pulse period and the duty circle to stabilize the output intensity at the value that Eve desires. This figure shows the hacking performance at different power. The purple point indicates that only 3 nanowatt injection power can lead to significant DC bias error. So as we know, compared with the BB84 QKD, MDI-QKD protect both the channel and the detection. So we hack MDI-QKD to demonstrate our IP attack. We demonstrate our attack in 2 different cases. In the first case, we assume Charlie is the eavesdropper, so he can control both of the channel and the bare state measurement. This is the hacking device. He injects a UV laser at 405 nanometer from the channel to user's source and control user's output intensity. Then he split user's quantum signal to two parts, one of which is detected by these two single photo detectors to project the quantum signal to the Z basis. If something is detected, he will record the result and announce the bare state measurement result normally. Otherwise, he always announces the bare state measurement is failure. In the second case, we assume Charlie is honest, so the eavesdropper is Eve in the channel. Because Eve cannot control the detection, she should insert an optical switch in the channel. And if Eve detects nothing, she will block the channel by the optical switch. So the two cases is actually equivalent. Here is the hacked MDI-QKD system, and we insert our hacking devices into the channel that links Alice and Charlie. This figure shows our hacking result. This figure indicates that we can control the output intensity by carefully tuning the injection time, pause period, and duty circle. We can maintain the intensity at the value we desire. And this figure shows the information leakage and final key rate. We can find, although over 99% row key bits are targeted by eavesdropper, the estimated information leakage of users are only 70 to 80%. The final keys are generated between Alice and Bob, although none of them is secret. The second topic I want to introduce is correlated intensity. The correlation is a very tricky problem in QKD field. It breaks the important IID assumption in security proof, so it is very dangerous to our implementation security. To address this problem, we propose three solutions from three different perspectives, from electronic, optical, and protocol. First, let's introduce the electronic perspective. We can compensate the voltage according to the current and previous selections. The step 1 and step 2 can be summarized as we should design a high-speed system to measure the correlation in real time. Here we design a single photo detector-based monitor. Compared with the previous monitors, our monitor have a higher speed and a better signal-to-noise ratio. And then we design a high-precision model for calculate the mean photo number, namely the intensity, from the SPD counts. Based on the above two steps, we finally design a feedback algorithm for suppressing the correlation. This figure indicates that our algorithm can finish the suppression in 10 iterations, and this figure indicates that the suppressed correlation are less than 1%. Before the suppression, the maximum correlation reaches 40%. Now our electronic solution has suppressed the correlation to 1% level. Our question is, can we suppress the much lower? Our answer is yes. We can design a correlation mitigating modulator. Okay, Here is the traditional commercial MDI-based intensity modulator. This figure shows the corresponding response curve. The point SD and V are employed to generate signal, decoy, and vacuum state respectively. We can find that the point D is located at a slope position, which means that the decoy state is very sensitive to the disturbance and noise. This table shows that in bandwidth limited case, the division of signal state is less than 1%, but the division of decoy state reaches 20%. Here we proposed a multi-pass MZI modulator. This modulator have multiple different stable points. So we can place all of the decoy signal and vacuum state on the stable point, so they would be insensitive to the disturbance. Besides, these stable points are tunable, so it satisfies the requirement of protocol optimization. The most importantly, this device is currently usable because we can use a commercial dual parallel MZI modulator to mimic a 3-pass MMZI. This is the response curve of the 3-pass MMZI. It has many stable points. It satisfies the 3 or 4 intensity in decoy state method. We test our devices by this setup. When employing a MZI modulator here, the correlation division reaches 20% level. However, when we employ our MMZI, the correlation division reduced to 0.1 level. The final solution is from protocol perspective. It's very difficult to consider correlation in security proof because the correlation makes the dimension for analyzing very large. In 2021, Professor Curti and his group proposed a solution based on the Cauchy-Schwarz inequality. They solved this problem, but the secret key rates are relatively pessimistic. In the next year, they find that if we add an assumption that Alice knows the distribution of fluctuation of each pattern, the secret key rate can approach to the ideal no correlation case. However, this assumption is very strict because it's difficult for us to require users to know the distribution of each pattern. But it's reasonable to require users to know the mean photo number. So based on this idea, we designed a new intensity correlation tolerant protocol. In this designment, the SPD monitor is part of the protocol. Alice should estimate information leakage with both Bob's announcement and her own monitor result. And with this method, we can find without the strict assumption, we can still approach to the no correlation secret key rate. Finally, I want to introduce an alternative resolution against the modulation loophole. We call it a fully passive QKD. Okay, now that most of the loophole and side channel come from the modulator, why don't we remove them in QKD system? Based on this idea, Professor Lu and Professor Curti proposed a fully passive QKD protocol. In this protocol, they remove all active modulators to avoid any loophole in active modulation. Based on their protocol, we solve many technical problems and design a time-being fully passive QKD, and we realized the first fully passive QKD experiment. This is the abstract of our experimental setup. It consists of a quantum module and a post-selection module. The quantum module consists of a GaN switch, laser diode, and some passive optical component and passive interferometers. The laser diode generates phase randomized pulses, and this part transfers the randomness on phase to randomness on intensity and quantum and timing state. Then the output state of this module is split to two parts, one of which is attenuated to single photo level to be sent to Bob, and another part is detected by the post-selection module for the post-selection. Here is our experimental setup. This is the quantum module. It generates it output random encoding on Bloch sphere and output random intensity from 0 to mu max. Here is the post-selection module. It post-select which basis, which state, and which intensity it belongs to. And this is our experiment result. It is in great agreement with the theoretical simulation. Thank you very much. Thank you for my collaborators and the QKD group at CIS Key Laboratory of Quantum Information. Thanks.
Thank you very much for the talk. Are there any questions? I see one over here.
Thank you so much for your great talk. I have a question about that. When you talk about correlated intensity, you say you use the feedback method to suppress the intensity correlated to 1% level, and you use MMGI to suppress it to 0.1%. Can you explain one more time that how it can do that?
As I have introduced, here we use a gradient decrease algorithm to first we measure the division of each pattern by our SPD based modulator, and then we calculate each pattern, the mean photon number of each pattern in real time. Based on this, the calculation result, our algorithm calculate how many voltage we should compensate, and we compensate the voltage not only based on the current selection, but only based on the current and previous selections. So we can mitigate the correlation to 1% level. Then here is our optical solution. This device has many stable points. Before in the commercial MDI modulator, the decoy state is placed at slope positions, so it is sensitive to the disturbance. But here we place both all of the signal decoy and vacuum state in stable point, so all of them are insensitive to the disturbance.
Okay, thank you. I have another question that you give a protocol that can help to solve the correlated intensity too, and I wonder that can we use this protocol and use the feedback method to make a better effect?
This is a good question. As a matter of fact, we can find the protocol performance relies on the correlation level. If we mitigate the correlation to a lower level, the protocol performance would be better.
Thank you.
Is there maybe one quick question before we move on?
Thank you very much for your presentation. Could you tell me, please, what do you see as a countermeasure against APA attack in case when protocol and optical scheme are already determined?
Do you mean what's our countermeasure against IP attack?
Yeah.
Okay. I think regarding this problem, I think first of all, we think the devices that are susceptible to are sensitive to EVE's attack should stay as far away from Alice's exit point as possible. Besides, if Alice use intensity monitor to monitor his output intensity, he can avoid the IP attack.
And what do you think about using another materials, or in case of lithium niobate, maybe some ions which can be induced into these materials? This can be used as a countermeasure or not?
Okay, this is a very good question. I think use other material can indeed avoid the IP attack. Thank you.
Okay, thank you very much.
Okay, sorry, if it's okay, maybe we can, you can take it offline because we, to keep on schedule, I think we should just thank the speaker one more time.
Thank you.